Uniform circular motion. So we're looking today at another example of a non-inertial reference frame, and it's the most common one that leads to people thinking about non-inertial force or non-inertial reference frame forces, fictitious forces, and thinking that they're real, basically. So I made a little video, posted here, so you can see what I'm talking about when I'm talking about horizontal uniform circular motion. This is just a padlock on a string and whirled around, slow motion so you can really see. Okay, so think about that as we're talking about all this stuff. And so here we go. With uniform circular motion, we're going to look at which way acceleration is as a first thing to start out with. And so it's kind of a back to basics approach here, where we just look at delta v. We want acceleration. Acceleration is delta v over delta t, right? So if we go back to basics here, we've got delta v equals v2 minus v1, and so that would involve a tail-to-tail vector diagram to help represent the vector subtraction to get delta v to help us get the direction of acceleration. And so in this scenario, you've got this is your initial and that's your final. So you can tell that's the direction of delta v. And yeah, so the average acceleration is delta v over delta t. And that would be at your like halfway point here, right? And so if you look at delta v, well, you're just basically multiplying by a scalar, right? So you're gonna have the same direction, it's just gonna be a different size. So if you look at the diagram here, you've got this average acceleration like that, right? So you can see that is towards the center, okay? So it is, which way is the net force? Well, the net force is in the same direction as the acceleration, so it's towards the center also. Yeah, so in uniform circular motion, acceleration is towards the center of the circle, and it's called the centripetal acceleration. It's just a special version of acceleration, so they have a name for it. It's kind of like with circles, they have special names for the distance across, diameter and so on, right? Distance around, perimeter, they call it circumference, like it just makes sense because it's kind of unique. And the force that's causing that acceleration, so net force, is of course the force that's causing an acceleration of a system. And so it has a special name as well. It's the centripetal force. So Fc is the centripetal force. Okay, so that's labeled there for us. All right, so circular motion, definitely one of the most difficult to experience without invoking a fictitious force belief. But note in this little animation, we've got the speed is constant the whole time. It's just kind of jumpy because it's an animation, right? But picture it jumping around at a constant rate. And the acceleration is always towards the center in the diagram, right? So picture the padlock on a string. The string is always pulling towards the center. If you go back and watch the video, right? So in this scenario here, you've got acceleration is always perpendicular to the motion at any given time, as you can see. So it's not changing the speed, it's just changing the direction, right? So it's constant speed, but of course not constant velocity, right? Because the direction is changing. This little animation is to help us think about something here. And so they've got, give it a second here, it'll start again. They've got two little balls or whatever in the diagram, or blue one and red one. So you watch here, the blue one continues going with a straight path until the red one starts to push on it, basically, is the idea of that, right? So I've got it freeze framed here where you can picture the, excuse me, the blue one continues in a straight line until it gets hit by the red one to make it turn, right? So it describes that. So you keep going, and then of course the door pushes on the person, and then like this is if you're like flopping around in a car, and or someone just takes a turn really aggressively, you'd end up getting slammed. You'd feel like you're getting slammed into them. In reality, like if you're the blue person, you'd feel like you're getting slammed towards the outside of the car, the outside of the circle. But in reality, you're just trying to go with a straight line motion. Really, the people on the outside of the circle are the ones that end up kind of slamming into you and making you finally make that turn, right? So that has to do with the idea of like which way a mass will go when you let go. Okay, so this little video that I made Sunday morning in my living room. Here we go. So at some point here, I just let go, and you can see the lock just continues on with a straight line motion, right? So close those so they don't start playing on you again by accident. So up here, actually, let's go with this one. At any given time, if you were to take a freeze frame of that, picture when it was right here, the velocity was straight up. And so you let go, it's going to keep going straight up. Okay? So frames of reference in circular motion. So if we look at the inertial frame of reference, then really there's just this net force towards the center, right? That net force towards the center is necessary to make it travel in a circle, and it is absolutely, it's a real force. It's the net force that's on the system. It's supplied by the tension force in the string, for example, and it's Fc. So centripetal force, right? And you can certainly think of this as a vector. It's just the vector is just kind of a weird one where it's just always towards the center, right? So instead of saying it's always left, well, it's left and then it's down and then it's to the right and then it's up and so on, and it just keeps repeating. If you're in this situation, so picture being in an amusement park ride, right? You're in a non-inertial reference frame. What would you feel inside of that? Well, you would actually feel you'd feel the wall pushing on you, and if that's necessary, just like right now, you have, presumably you're sitting down probably somewhere, and you feel the force of the chair up on you, and of course you think of that as because it's opposing that gravity force, right? And so in this scenario, that's absolutely the kind of thing you're thinking about here, is that you feel this force on you, but it's your brain is saying, oh, that's because it's the chair, or the wall of the amusement park ride is fighting against that force that's pushing you outward, okay, or pulling you outward. That force is called a centrifugal force. Okay, so it's a center fleeing force. It's outward. Okay, that one doesn't actually exist, but it absolutely makes sense to draw in the context of that non-inertial reference frame. Okay. The lesson from my grade 11 class, really, there on Earth, we're basically in a non-inertial reference frame all the time, and that force that that the chair is fighting against is really gravity. And so there's a lesson from the 3U course that's on my YouTube channel, that talks about how gravity is not really a force, not a real force, and that's probably a weird thing for you to hear if you haven't ever heard it before. Go back and watch the video to do with it, and you'll see what I mean. But basically, it's the same as this. It's on Earth we're in a gravitational reference frame, which is essentially a non-inertial reference frame. Understanding that idea, by the way, is critical to understanding Einstein's theory of general relativity, which makes amazing predictions, and it has for probably a century almost, that allows us to have things like GPS navigation. So it is definitely true. The calculations work, at least you could say. Anyway, so circular motion, specifically, uniform circular motion. So you're in a constant speed in a circular path. And so your velocity is not constant, as I said already, because your size and your direction is the velocity. And of course, the direction is changing, and it's changing towards the center of the circle all the time, which is your centripetal acceleration. And so there needs to be a force towards the center all the time to cause that, right? So this is what's really going on, but it's hard for people to shake their feeling and their preconception or their idea that you've had in your head for a long time, right? That you're actually getting pulled outward. So it feels like you're accelerating outward, or your body wants to accelerate outward. But the circus ride or whatever, is pushing in to balance that, right? So it's a very logical conclusion. It's just unfortunately kind of wrong, right? So yeah. If you let go of a ride, there's a slide later on, but you let go, you just go in a straight path. You don't go outward. You go on that tangent velocity. So the previous page is the inertial frame, reference frame analysis, right? This now we can look at. So this is when uniform circular motion is happening relative to Earth. And so we have this scenario here, right, where you've got this centripetal force that acts towards the center, the acceleration is towards the center, your velocity is tangent to the circle. Without an applied force, the object is going to go in a straight line, and so on. All this stuff. We can talk about a non-inertial reference frame. And so within that ride at the the fair or wherever you are, in that ride, basically you have no acceleration relative to the seat that you're strapped into in the ride that you're on, right? So in that case, you have this applied force towards the center, and you have this centrifugal force out, right? And so they're balancing to give you that zero acceleration, right? So there we go. Yeah, and so relative to that ride, you would go outward, but it happens because as the ride rotates, let me show you here, as the ride rotates, just like say here, right? You would have kept going in a straight line and you'd end up out further from where you started. You think of it like that. Okay. So it absolutely does lead to the observation of moving outward relative to the rotating ride itself. So both of the descriptions are true. It just depends on what reference frame you're thinking about, right? So all of these, circular motion things that you're familiar with, right? Is just the merry-go-round ride, anyways, for now. So this little girl's holding on for dear life, laughing, having a great time, holding on to fight against that centrifugal force that's pushing her out, which is a real effect within that non-inertial reference frame, right? So what's really going on, of course, is she's holding on to apply force towards the center of the circle, right? Which causes an acceleration in the center, keeps her traveling in circular motion, right? So the free body diagram for the girl relative to the Earth is really just of an applied force towards the center, right? That centrifugal force is a fictitious force relative to the Earth, right? If she lets go, then she just keeps going in whatever velocity she had at that instant, right? So if she let go here, she would just go straight north. She has inertia. She had a velocity north. There's no force acting on her anymore. She's going to stay going north. You might have seen in previous questions, this idea of a ball, a little marble rolling around a track. Which path would it continue with after the track ends? So some people think like, oh, it's going to keep traveling in a circle because it was traveling in a circle, which is definitely not true. Some people think it would like fling outwards because of that feeling of the idea of this force that's pushing you outwards. In reality, of course, it would just keep going straight, right? As you're looking for information around the internet and the world and everything else, you're probably going to have common thoughts, from people creep in that aren't correct. So this description of a merry-go-round, you're holding on, or else you get thrown off. Well, thrown off would give you this idea of thrown outwards, right? In reality, you'd be like, well, no, you'd keep going tangentially, not radially outward, right? The centrifugal force pulls spinning things out towards the outside of the circle. It'll be like, no, actually, there's a centripetal force towards the center and so on, right? Holding a bucket full of water. We're going to analyze that next here. So just skip to it, but I guess you have a bucket of water, whirling around, and so the water has inertia. It wants to keep going, so it's being pushed towards the center of the circle all the time, making it travel in a circular motion. And so let's analyze that scenario. Okay, so you've got the water in the bucket, and my free body diagram is going to be for the water itself. And so we're trying to spin the bucket so that it has uniform circular motion. If the circular motion is fast enough, the centripetal force needed is greater than the gravity force, and so you'll see that the object will stay in uniform circular motion in the bucket and not fall out of the bucket. I wanted to mention somewhere in here maybe I deleted it. I might have deleted it, but in vertical circular motion, the only way to have true uniform circular motion is to be attached by like a rigid rod, like a post or something holding it, right? Like an arm or whatever holding it. Because of course, think of this scenario here. Gravity is going to make, if you're on a string and just whirling it around and around, gravity is going to make it speed up here, right? And then slow down here. So in the homework question, I actually deal with that by saying it's this object on a string has average circular motion. I might have to. This is an old version of this. Oh, there we go. This is the string version here. So different question. So this is the string here, and it's got average uniform circular motion. And so it's okay that it speeds up a little this way and slows down a little bit this way, because on average, And so I have like in this one of these questions, it has like, at that instant, what force would be needed or whatever the question is here, right? So hopefully that's okay for you. Get to it, it'll make more sense, hopefully. Here we go. So free body diagram for this thing. Well, free body diagram for the water here, right? We just have the gravity force on it is the 10 newtons. If we have, if gravity force is a certain amount of mass, gravity is 10 newtons. And if we need a centripetal force of 30 newtons, and this is where I'm going to start to stress the idea that the centripetal force is the net force. So you're not going to list the centripetal force in as a force here as one of your forces, because it's the result of all of those forces added up, right? So the centripetal force, you'll see in some work later in the lesson here too. I should try and show it really clearly where this is going to be F net, and then in the next line is going to be FC, right? And the next line is going to be the minus 30. Okay, so the net force is that. You can't list your net force that is the result of all the forces you're adding up as one of the forces you're adding up. Okay, so just make darn sure you catch on to that here. Like this is FC, right? You can't put FC here because that wouldn't make sense. You'd have all of, that is all of the force added up. That doesn't make sense to put it there. Right, but it's a super common mistake that I want to make sure you see not to do. And so in this scenario here, there's going to be a normal force from the bottom of the bucket pressing on the water down, right? So the bucket itself is essentially accelerating downward faster than the water wants to accelerate down. And so the water stays in the bucket. Okay, it's the best way to put it. So essentially it's held in by that 20 Newton force. The centrifugal force of 20 newtons is what you're going to kind of interpret that as, right? So in a vertical circular motion situation, you'll see that how much you feel like you're getting thrown outwards changes, right? It's the least at the top and it's the most at the bottom. Whereas in horizontal, we have a question I'll analyze for horizontal. It's just, you feel the same outward force the whole time. So at the bottom, our free body diagram work would lead to this, right? So we know we have the gravity force on there, and then we want a net force up, right? So we know the net force up is that centripetal force, so it needs to be plus 30. So now we have this minus 10 of gravity still, and add to both sides, you get your normal force of 40, and so you got this larger force, right? So this is where you're gonna feel like lots of, you're gonna feel lots of force on you towards the center, and so you're gonna interpret that as it's fighting lots of force trying to throw you outwards in that non-inertial reference frame, right? Yeah, so summary of the stuff. Centrifugal force is that perceived outward force associated with circular motion. So centrifugal. The centrifugal force is one of several fictitious forces, also known as non-inertial forces, because they make sense to list in non-inertial reference frames. So these forces don't actually exist, but they seem to. They make sense to talk about them in non-inertial reference frames. Of course, what's really going on is inertia, right? The fact that you're observing with respect to a non-inertial reference frame is what tricks you. So yeah, you definitely can include these forces in those non-inertial reference frames, and they have real effects. So this little video here of water in an aquarium spinning, you can see there's a real effect on these things. I think it's going to make us watch an ad first here. 1 second. Come on.
Got flavor block? Get spicy with Bothwell cheese.
I just go for my files, but it's probably quicker just to put up with the commercials here. One more. Come on. Oh, what? What's going on? Oh, I was holding, turning the volume down, so it was
EQ trouble. Bank is here to help you make bank, and it seems that's been making sense to Canadians.
So I didn't like that I was turning the volume off. Anyways, all that just to show you this little aquarium that's spinning around, right? And you can see the real effect on the water, of course, in that non-inertial reference frame. So eventually here, right? That's what all that waiting was for. And the next thing here, that's just about the idea of if you cut the string, the ball would just go with the current velocity it has. I really don't like actually if they have this curved velocity thing here, like they're that, really a velocity like that at any given instant. You cut the string and then they would just keep going in a straight line. So the point of that is just where I scanned that picture from. I didn't edit out that silly curved arrow. And you want to see the extreme merry-go-round? It's ridiculous. Let's go to my videos here. Please don't do this. Videos, extreme. Extreme merry-go-round. Here we go. I just open automatically here. For my files, we can avoid another commercial delay. So they've got a car. They've got a car hooked up to a merry-go-round. They have two guys, they're buddies on this merry-go-round, and they spin it, and it looks painful, like real fast. And they have a hard time, like, stopping it at that point without like decapitating the person. Like I said, don't do this, right? But yeah, not safe. But in that scenario, there still isn't any outward force. Like it's just a force needed towards the center to cause that circular motion. If the person let go, they would have just flown off in a straight line with whatever velocity they had at that instant, right? This one's really cool here, the sword reference frame thing. Let's go videos. Where am I at here? Sword. And it's again kind of along the lines of that old video that I hope you watched a lot of. You just get messed up by reference frames. Like your experience of being inside of a circular reference frame is disorienting, and you start to think there's other forces going on, right? So in this one here, that thing. So you want to put a camera at the end of a meter stick and swing it around like a sword. What does it look like? So you'll see and it's pretty hard to interpret what the person's doing if they look at all the different motions. Beauty of this video is they show a side by side in a minute of what the person's really doing. So you can see basically right now you're in that non-inertial reference frame. So you have to explain all these twists and turns by forces, right? In reality, you can see from the Earth reference frame coming up here, the third person perspective, the Earth reference frame. It just gives you a sort of a visual feel of the kind of effect of being in a non-inertial reference frame. Think about those non-inertial or these fictitious forces that you interpret being on you, causing all this weird observation, right? So just kind of neat. All right, back to lesson file here. Yeah, again, if an object's in uniform circular motion, then Fnet is the centripetal force. Do not put that thing on a free body diagram, right? It's your centripetal force is your net force, right? And so you'll see that in action on really the next slide. This one's easier because it's just horizontal stuff, right? So at position 1, what's the free body diagram? Horizontal, this is the padlock sliding on the floor. So the vertical stuff we're not talking about because it doesn't matter. You got the gravity force and the floor, normal force balancing out. So just really it's an X direction force we're talking about, which hopefully you're identifying here would be down, right? And that is your net force, right? That's the only force on the object horizontally. So let's go F net X direction and be like, okay, what all is there? Well, there's literally just the tension force. And we know that the net force is the centripetal force. And so the tension force is the centripetal force, right? That same writing would happen really for all of these you're going to see, right? So at position 2, obviously that tension force is up, so it's a centripetal force towards the center of the circle. Position 3, it's going to be to the right. Position 4, it's going to be to the left. At position 5, there's going to be an angle, right? And so if you're looking at values for if there's gravity involved, we're going to be doing components to do with because there's going to be another value that we have to combine, right? But in all of these, you can see very easily that the tension force is really just the net force, and so it's the centripetal force. And again, you can put vector bars on these things if you want, because there's a definition to do with the direction, right? It's towards the center of the circle. You just can't label it as north at a particular north or south. That's always, because it changes so much. So the weirder one here, here's the note that I was talking about earlier. I couldn't remember where it was. So with vertical uniform circular motion. And so note, this is really only can happen if you've got it attached to like a rigid rod, mechanically moving in circular motion, but really a string kind of speeds up and slows down and averages out. So it's still kind of sort of, you could still think of it as a string anyways, really. But let's just analyze things out. So at position 1, right? Similar to what we saw earlier in the lesson, position 1, we've got the net force is the centripetal force. So it's definitely down of 10 newtons. So it's in the wording here that we have this centripetal force of 10 newtons. Or I could have given a mass, and whatever the mass is that you multiply by 9.8 gives you 10. So it'd be like a mass of 1.1 or something like that, right? So we got the centripetal force is minus 10, while the centripetal force equals the gravity force plus the tension force. And so if the gravity force was 7 newtons, then you can see that the tension force would only need to be 3 newtons down. Okay, so this is moving fast enough that it would stay in uniform circular motion on average, speeding up and slowing down. But it wouldn't, the mass wouldn't drop out of this circular path. If you went too slow, it would, right? Because you'd have, the tension force. Maybe I should do that right now. I'll do it in a bit. So at position 2, you've got, the calculations here and the resulting net force and so on. You'd have your net force is your centripetal force, of course. So it's plus 10 in this case because it's up. And you have the gravity's down, and so they add up in this case, and you get this larger tension force, right? So I've gone and I've modified this force on this diagram to match mathematically. I didn't necessarily know that it was a bigger force than the gravity force. You go in and make it true afterwards, right? You just know there's forces, but the sizes come out of the calculations. In position 3, you've got the gravity force, but really the only thing that matters in the x direction of the acceleration, like at this position right here at 3, you'd want to say, okay, well, the x direction here is the direction of acceleration, typically is what we would do, right? And so now my net force equation, is interested in this x net force, in which case the gravity, you can see, isn't relevant, right? And so really you just get this situation where you've got the tension force is the only force in the mix, and so it's the only one you're talking about. Let me just go like this, right? So you'd have the friction, or the centripetal force would be this 10 Newton force towards the center, and it would be equal to just the tension force. This is just showing that you could add up with whatever other forces there are, but there aren't any in that direction. Position 4 is identical to that, just the opposite direction. And finally, position 5. Okay, this is the one we got to make sure to do a good job with here, right? And so position 5, you've got a reference frame direction, so accelerating towards the center. So we're going to make that be our x direction. So you can see I have like acceleration labeled that way. In other words, what I'm really saying there is that's my positive x direction. And so we're looking at the fact that this thing is in uniform circular motion. And so the acceleration is towards the center, right? Your net force is also then towards the center. So in that x direction, we've got a positive 10 newtons. The gravity force, you can see, would have a component outward, right? And so that's going to be in as that component. So it's adjacent to that angle. And so, cosine of the 69 degrees. Now notice I have a 69 degrees there. If you look at the 21 to the horizontal, the 21 to the horizontal would be purple here. The 21 to the horizontal would be here, which would leave this as being the 69 degrees, right? So yeah, cosine of that gravity force gives you the component, and so you've got that value as a a negative 2.59, comma by accident there. Add that to both sides, and you'll see you've got a tension force of 12.5 newtons. Okay. Let's go with the if it's too slow. So position 1, too slow. At position 1 with the velocity, speed, I guess, whatever, of the motion too slow. What happens, right? So let's say, now I did it just in terms of forces here, right? So say we're going so slow that the centripetal force is only 5 newtons, right? So if you're going so much slower that the centripetal force needed is only 5 newtons. So Fc for uniform circular motion is only 5 newtons. Let's do the free body diagram. We've got the diagram at that top of the circle business, right? We've got the gravity force, and we're thinking of like there's a tension force on here of some sort, right? So let's just sort of put it here as like Ft. We should look for what that thing is going to be. So in our free body diagram, you can see there's forces in that. So we're going to go, okay, the net force then is the centripetal force, right? Net force equals all the forces added up. And so there's a gravity force and there's a tension force, right? So we have the gravity force in like it was, which was 7 newtons. So we've got the -7, right? The -7 in, because I'm just going to use up as positive because that's what I'm more comfortable with. And then the tension force, you look at it and you say, okay, well, we're going to solve for that, right? The centripetal force we're finally going to put in here is that as that down of 5 newtons, right? So the down of the 5 newtons that we want. So in this case, it's down is where we are in the circle. And so we have the math is looking like this. So we're going to add 7 to both sides. And we're going to end up with that tension force being 2 newtons, right? Positive 2 newtons. So you can tell that positive 2 newtons in this case means up, right? And so really what you're looking at there is if this thing was attached by a string with its average uniform circular motion and so on, that string would be trying to push up on this mass. And there's a saying in engineering that you can't push on a rope, right? So can't push on a rope is a super common saying in engineering. Basically, you gotta watch for if your situation where you're bracing something, you have to make sure that you know for sure what direction the force is going to be. Make sure you're not relying on a cable or a rope to push, right? And this actually happened. My brother-in-law is an engineer. He went to U of T and he's an engineer. And so he was they're working on engineering for a pipeline that was underwater. And the curve of the pipeline, the way it was set up and so on, it was braced by cables, and it kept rupturing, it kept breaking, and they couldn't figure out why. And he's like, and eventually he's looking at the vector diagram for it and so on, and he realized, oh my gosh, this is literally a you can't push on a rope situation. They had it braced by a cable, assuming the force was going to be a certain way and it would work against it. But because of weird complications in the pressure and the way the fluid mechanics works in the pipe, it was actually the other way, right? And I think they had said, oh, they look at the numbers and be like, okay, it's fine, there'll be a force there. But when they look more carefully at the directions that cable was supposed to be pushing, which of course cables and ropes and things like that can't do that, right? If this thing was connected by a rigid rod, then of course this thing could have uniform circular motion at any speed. It's just the rod would be pushing up at the top instead of pulling towards the center. Okay. So that is, uniform circular motion. You've got classic kind of questions. The first couple are just kind of definition ideas, right? The first 4, I think, are not calculation based. Down here, the kind of calculations we just did in class. Notice I gave you the mass and the accelerations instead of the forces. Well, obviously just MA, right? gives you the forces, so that shouldn't be a stumbling point. Bit of a challenge question down here to think through. At a slower speed, right? If you're at too slow of a speed for this thing to stay in the circle, if it's a string, at what angle could it, if it was in circular motion, say you're moving it in circular motion and you just let go, right? So you're moving this thing deliberately with your hand in circular motion. Up here, you're going to be slow. So if you let go, it wouldn't stay in the circular path. It would start to drop down quicker, right? If you're moving it in circular motion, at what angle to the horizontal would it have to be so that if you let go, it would then do its uniform circular motion thing naturally because of the gravity and whatnot effect? That's this question here. I felt like I should communicate the idea of it a bit more as to what it's asking. Yeah, and here, of course, we already did in class the idea of like what that's, especially if you analyze for position 3, it should be very obvious. Position 5 is just a little harder because of components, right? But how would the situation change if it was at a slower speed, right? This thing's attached by a string, right? And so you should be able to work that out and describe what would happen. Yeah, so that is it for that. As always, thanks for watching. Let me know if you have any questions, and I'll see you next time.